You think the border is just a line, a boundary, an edge, the place where one thing ends and another begins, an upward. Simple, clean, draw a circle, the border is obvious, inside the circle, outside the circle, and a thin line separating them. That's how borders work, right? Wrong. When you look at the Mandelbrot set, when you really look at its edge, you discover something that demolishes everything you think you know about boundaries. The border of the Mandelbrot set never stops. It never settles. It never becomes a simple line, no matter how closely you examine it. Most people have seen the Mandelbrot set, that famous black shape with its bulbs and tendrils surrounded by psychedelic colors. They look at it and think they understand. The black part is inside, the colored part is outside. The border is where black meets color. Simple. But that's not an answer. That's just describing what you see at low resolution. When you actually zoom into that border, when you magnify it 1,000 times, 1,000,000 times, 1,000,000,000 times, something impossible happens. The border doesn't get simpler, it gets more complex. Always, without limit, forever. The border never stops, because the border isn't a line at all. The border is an infinite universe unto itself. Let me show you what I mean. Start with what the Mandelbrot set actually is. Take a complex number C, any point on the plane. Apply a simple rule. Start with 0, square it, add C. Take the result, square it, add C again. Repeat forever. Because for some values in bigs of C, this process stays bounded. The numbers bounce around, but never escape to infinity. Those points are inside the Mandelbrot set. We color them black. For other values of C, the process explodes. The numbers grow larger and larger without limit, escaping to infinity. Those points are outside the Mandelbrot set. We color them based on how quickly they escape. The border is supposedly the boundary between these two behaviors. Points that stay bounded on one side, points that escape on the other, should be simple, should be a curve, maybe a complicated curve, but still just a curve. It's not. Here's what happens when you approach the border. Deep inside the Mandelbrot set, far from the edge, behavior is predictable. Start iterating and the numbers quickly settle into a pattern. They might converge to a single point. They might cycle between two values or 4 or 8, but they stabilize. They become predictable. The interior is calm. Deep outside the Mandelbrot set, far from the edge, behavior is also predictable in its way. Start iterating and the numbers immediately start growing. They escape to infinity quickly, decisively, no ambiguity. The exterior is also calm in its own fashion, but near the border, something completely different happens. Near the border, tiny changes in position create enormous changes in behavior. Move a millionth of a unit in one direction, the point escapes to infinity. Move a millionth of a unit in another direction, the point stays bounded forever. The fate of the iteration depends on the exact position with incredible sensitivity. This sensitivity is not a bug, it's not a limitation of our measurements. It's fundamental to what the border is. Think about what this means. At every point along the border, there are bounded points arbitrarily close by, and there are escaping points arbitrarily close by. No matter how small a region you examine, that region contains both types of points intimately mixed together. How can you draw a line separating them when they're infinitely intermingled? You can't. That's the point. The border isn't a line. The border is a fractal dust of infinite complexity, a zone where bounded and unbounded behaviors are woven together at every scale. Let me make this concrete. Pick a point exactly on the border. Now draw a tiny circle around it as small as you like. Inside that circle, you will find points that escape and points that stay bounded, always, no matter how small the circle. Now pick any point inside that circle that escapes. Draw an even tinier circle around that point. Inside that tinier circle, you'll find points that stay bounded and points that escape. This continues forever. At every scale, bounded and escaping points are interleaved. The border isn't a line you can draw. It's a pattern that exists at every level of magnification, never resolving into something simple. This is why the border never stops. Every time you zoom in, expecting to finally see a clear separation, you find more mixing, more complexity, more structure. Now here's where it gets truly strange. The border isn't just infinitely complex, it generates new structures at every scale. Zoom into the border of the Mandelbrot set. What do you see? Spirals, tendrils, seahorse tails, elephant valleys, and scattered throughout baby Mandelbrots. Tiny copies of the entire set, complete with their own bulbs and tendrils embedded within the border region. These baby Mandelbrots aren't decorations. They're not coincidences. They emerge inevitably from the mathematics. Every one of them is connected to the main set by infinitely thin filaments. Every one of them has its own border, its own infinite complexity, its own baby Mandelbrots within its border. The border contains copies of the whole. And those copies contain copies. And those copies contain copies. Self-reference at every scale, structures quoting structures, patterns containing patterns. But here's the crucial point that most people miss. The baby Mandelbrots aren't exact copies. Each one is unique. Each one lives in a different neighborhood of the border, surrounded by different spiral structures, connected by different filaments, embedded in a different context. The border produces infinite variety, not infinite repetition. Every zoom reveals something you've never seen before. Familiar themes in unfamiliar arrangements, recognizable patterns in unprecedented configurations. This is why mathematicians have been exploring the border for decades and still finding new phenomena. The border is not a static object to be mapped. It's a generative process that produces structure without end. Why does this happen? What makes the border so different from the interior? The answer lies in Ninish Husser, the nature of iteration and sensitive dependence. Inside the Mandelbrot set, iterations converge. They settle down. Small differences in starting position lead to small differences in final behavior. The system is stable, predictable, forgiving, but on the border, iterations neither converge nor escape. They hover on the edge of both behaviors. They're balanced on a knife's edge between stability and explosion, and balanced systems are sensitive, incredibly sensitive. A perturbation that would be absorbed in a stable system gets amplified on the border. Small causes lead to large effects. Microscopic differences in position lead to macroscopic differences in fate. This sensitivity is what generates this complexity. The border is where the iteration process cannot decide, should this point escape or stay bounded? The mathematics hesitates, and in that hesitation, in that inability to cleanly separate the two behaviors, infinite structure emerges. Think of it this way. The border is not a place. The border is a question that the mathematics cannot answer simply. The question is, does this point escape or not? For points deep inside or deep outside, the answer comes quickly. But for points on the border, the answer requires infinite computation. It depends on infinitely precise information about the exact position. That infinite precision requirement is what makes the border infinitely complex. You can never have enough information to fully characterize it. Every additional decimal place of precision reveals new structure that was invisible before. Here's another way to understand this. The Mandelbrot set is defined by a limiting process. You iterate forever and ask, does the sequence stay bounded? But you can never actually iterate forever. You can iterate 1,000 times, 1,000,000 times, 1,000,000,000 times. But finite iteration only gives you an approximation. For points deep inside or outside, a few hundred iterations are enough. The behavior is clear. But for points on the border, even 1,000,000,000 iterations might not be enough. The point might look like it's staying bounded for 1,000,000,000 iterations and then suddenly escape. Or it might look like it's about to escape and then suddenly stabilize. The border is where the limit is hardest to compute, where finite approximations are least reliable, where you need infinite precision to know the truth. This is what I mean when I say the border never stops. It never stops revealing new structure. It never stops surprising you. It never stops requiring more precision, more computation, more investigation. Now, let me tell you something profound about what this means for mathematics and nature. Classical mathematics loves the boundaries, clean separations. This region has property A. That region has property B. The boundary between them is a well-defined curve. Inside and outside are cleanly delineated, but the Mandelbrot set shows that boundaries can be infinitely more complex than the regions they separate. The interior of the Mandelbrot set is relatively simple. It's a connected region with a definable area. The exterior is also relatively simple. It's everything else. But the boundary between them, the boundary is where all the action is. The boundary is infinitely complex. The boundary has infinite length. The boundary contains miniature copies of the whole set. The boundary generates new structure at every scale. The boundary is not the boring part, the boundary is the interesting part. This inverts how we usually think about things. We tend to focus on interiors, what's inside the circle, what's inside the country, what's inside the cell. Boundaries are afterthoughts, just the edges where things end. But the Mandelbrot set teaches us that boundaries can be where the real complexity lives. The transition zones, the edges, the places between categories, those might be the richest, most structured, most interesting regions of all. Think about where this applies in nature and life. Phase transitions, water becoming ice, liquid becoming gas. The transition isn't a simple boundary, it's a complex zone where both phases coexist, where fluctuations are large, where interesting things happen. The boundary between phases is often more complex and more interesting than either phase alone. Coastlines, the boundary between land and sea, not a simple line. An infinitely intricate fractal curve with structure at every scale. Bays within bays within bays. The coastline is more complex than either the land or the ocean. Ecosystems, the boundary between forest and grassland, the boundary between water and land. These edge zones, ecotones, often have more species diversity than either ecosystem alone. The boundary is richer than the interiors. Human knowledge, the boundary between what we know and what we don't know. That's where the interesting questions live. The interior of established knowledge is settled. The exterior of complete ignorance is empty. But the boundary, the edge of understanding, that's where science happens, where discoveries are made, where complexity resides. The Mandelbrot set is a mathematical proof that boundaries can be infinitely complex, that the edge between simple categories can contain more structure than the categories themselves, that transitions and borders and edges might be the most important region to study. Now let me return to the specific mathematics. Why do new structures keep appearing as you zoom in? Why baby Mandelbrots? Why spirals and seahorses and elephants? The answer involves how the iteration process behaves near different types of boundary points. Some boundary points are periodic. The iteration at these points eventually cycles back to itself. Period 2 points cycle between two values. Period 3 points cycle among three. Period n points cycle among n. Near these periodic points, the boundary has characteristic structures. Near period 2 points, you get the main cardioid bulb. Near period 3 points, you get specific decorations. The spirals and seahorses correspond to different periodic behaviors. And here's the key. As you zoom deeper into the boundary, you encounter regions where the periodicity changes, where period 2 behavior transitions to period 3 or period 5 or period 127. And at each of these transitions, the structure of the boundary changes character. The baby Mandelbrots appear at places where the mathematics resets, where the local behavior recapitulates the global behavior, where the part mirrors the whole. But each baby Mandelbrot is embedded in a different context. The surrounding spirals and decorations are different. The periods involved are different. The connectivity is different. So while the baby Mandelbrot is recognizable, its neighborhood is unique. This is deep self-similarity without exact repetition. The border quotes itself constantly, but never repeats. Every zoom reveals the same themes, but different variations, like a fugue that uses the same motifs, but develops them in ever new ways. And because the periodic structure of the border is infinitely complex, because there are infinitely many different periodic behaviors all interleaved along the boundary, the border itself is infinitely complex. There's always another period to transition to, always another structure to discover, always another baby Mandelbrot hiding in an unexplored corner. The border never stops because the mathematics never runs out of new behaviors to exhibit. Here's something that should shift how you see boundaries forever. The border of the Mandelbrot set has zero area. You can prove this mathematically. Despite its infinite complexity, despite containing infinitely many baby Mandelbrots, despite having structure at every scale, the boundary is too thin to have measurable area. Yet the border has infinite length. If you tried to measure its length with a ruler, you would get infinity. The finer your ruler, the more length you'd measure. The length diverges. So we have a set with zero area and infinite length, a curve that's infinitely long but takes up no space. This seems paradoxical until you realize that the border isn't a curve in the classical sense. It's a fractal. It has a dimension between 1 and 2, more than a line, less than a plane. The fractal dimension of the Mandelbrot boundary is exactly 2. This means it's as complex as a boundary can possibly be while still being a boundary. It's maximally complicated. It fills space as much as a curve can fill space without actually becoming a surface. This maximal complexity is another reason the border never stops. It's not just complex, it's as complex as mathematically possible. Every bit of the boundary is equally intricate. There are no simple regions, no places where the structure calms down. Complexity everywhere, at this, every scale, at every location. Let me close with what this means for how we understand mathematics and the world. When I first saw the Mandelbrot set rendered on early computers, I was struck by something. Here was a mathematical object defined by the simplest possible rule. Square and add, a child can understand it. Yet the boundary this simple rule produces is infinitely complex, more complex than anything we could design, more intricate than anything we could draw. The complexity isn't put in by hand. It emerges from iteration, from feedback, from sensitive dependence. The rule is simple. The boundary is infinite. This taught me something profound. Complexity doesn't require complicated rules. Complexity can emerge from simplicity through repetition, through iteration, through the accumulation of small effects over many steps. The border of the Mandelbrot set is proof. One rule iterated forever produces a boundary that never stops revealing new structure, a boundary that contains its own image at every scale, a boundary that is simultaneously zero area and infinite length, a boundary that is as complex as geometry allows. The boundary isn't where mathematics stops, the boundary is where mathematics comes alive. Classical mathematics saw boundaries as afterthoughts, the edge of a region, the line where something ends, boring, secondary, derivative. Fractal mathematics sees boundaries differently. Boundaries are where the action is, where stability meets instability, where order meets chaos, where simple rules produce infinite complexity. The Mandelbrot set taught us this. Its border taught us that edges are not endings, edges are beginnings, edges are where the infinite hides. When you see that famous image, don't look at the black interior, don't look at the colorful exterior, look at the boundary between them, that infinitely thin, infinitely complex, infinitely generative zone where the border never stops. That's where the mathematics lives. That's where the beauty resides. That's where the infinite tensions, complexity of simple rules reveals itself. The border never stops, and that's exactly why it matters. Not comfort, not simplicity, truth,